Okay, let's dive into this problem about conserved momentum in a Lagrangian system. So here's our problem statement. We are given a Lagrangian which describes the dynamics of our system. You can see the expression there, L equals 1 half m times the quantity x dot squared plus y dot z dot plus z dot squared, all of that, minus alpha times the quantity 2x plus 3y plus z. And the question asks us to find the conserved momentum for this system. We are given 4 options for what that conserved momentum might be. We need to figure out which of these, if any, represents a quantity that is conserved over time. Let's start by talking about what a conserved quantity is in this context. Basically, a quantity, let's call it Q, is conserved if its total time derivative is 0. So dq by dt equals 0, it doesn't change over time. A really important concept related to this, especially in Lagrangian mechanics, is canonical momentum. The canonical momentum pi corresponding to a generalized coordinate qi is defined as the partial derivative of the Lagrangian L with respect to the velocity of that coordinate qi dot. That's pi equals the partial of L with respect to qi dot. Now, a key result often seen as a specific case of Noether's theorem tells us that this canonical momentum pi is conserved if the Lagrangian does not explicitly depend on the coordinate qi itself. In other words, if the partial derivative of L with respect to qi is 0, then pi dot is also 0, meaning pi is conserved. Let's calculate the canonical momenta for each of our generalized coordinates x, y, and z. Remember, the formula is pi equals the partial of L with respect to qi dot. First, for x, we calculate px, which is the partial of L with respect to x dot. Looking at our Lagrangian L, the only term depending on x dot is that 1 half m times x dot squared. Taking the partial derivative with respect to x dot, we get 1 half m times 2x dot. The 2's cancel, leaving us with m times x dot. So px equals mx dot. Continuing with our canonical momenta calculations, next for y, we calculate py, the partial of L with respect to y dot. Looking at the Lagrangian, the only term with y dot is the 1 half m times y dot z dot term. When we take the partial derivative with respect to y dot, we treat z dot as a constant. So the derivative is 1 half m times z dot. Therefore, py equals 1 half mz dot. And finally, for z, we calculate pz, the partial of L with respect to z dot. In the Lagrangian, we have two terms depending on z dot, 1 half my dot z dot and 1 half mz dot squared. Taking the partial derivative with respect to z dot, we get 1 half m times y dot from the first term plus 1 half m times 2z dot from the second term. This simplifies to 1 half m times the quantity y dot plus 2z dot. So pz equals 1 half m times the quantity y dot plus 2z dot. Now let's calculate the generalized forces. These are given by the partial derivative of the Lagrangian L with respect to the coordinate qi itself. First, for x, we calculate the partial of L with respect to x. Looking at our Lagrangian, the only term with x in it is the minus alpha times 2x term. The partial derivative with respect to x is simply minus alpha times 2, which is minus 2 alpha. So the partial of L with respect to x is minus 2 alpha. Notice this is not 0, so px is not conserved by itself. Let's find the generalized forces for y and z. For y, we calculate the partial of L with respect to y. The only term in the Lagrangian with y is the minus alpha times 3y term. Taking the partial derivative with respect to y gives us minus alpha times 3 or minus 3 alpha. So the partial of L with respect to y is minus 3 alpha. Again not 0, so py is not conserved alone. For z, we calculate the partial of L with respect to z. The term with z is the minus alpha times z term. The partial derivative with respect to z is minus alpha times 1, which is just minus alpha. The partial of L with respect to z is minus alpha. This is also not 0, so pz is not conserved alone. Using the Euler-Lagrange equations, we see that the rate of change of the canonical momentum p sub I dot is given by the partial derivative of the Lagrangian with respect to the generalized coordinate q sub I. This represents the generalized force. From our previous calculations, we determined the time derivatives of the canonical momenta. For the x component, p sub x dot is minus 2 alpha. For the y component, p sub y dot is minus 3 alpha. And for the z component, p sub z dot is minus alpha. You can see the full derivations on the slide. Since none of these are individually 0, these momenta are not conserved. We hypothesize that a conserved quantity, p, might exist as a linear combination of these momenta. P equals c sub x plus c sub y p sub I plus c sub z. For this total momentum p to be conserved, its time derivative p dot must be 0. This implies that the sum of c sub x times p sub x dot plus c sub y times p sub y dot plus c sub z times p sub z dot must equal 0. Now we use the Euler Lagrange results we just found to find the condition on the coefficients Cx, Cy and Cz for p dot to be 0. We substitute the expressions for px dot py dot and pz dot into the equation Cx px dot plus Cy py dot plus Cz pz dot equals 0. This gives us Cx times minus 2 alpha plus Cy times minus 3 alpha plus Cz times minus alpha equals 0. Assuming alpha is not 0, we can divide the entire equation by minus alpha. This leaves us with 2cx plus 3cy plus cz equals 0. So any quantity p that can be written as a linear combination cx px plus cy py plus cz pz, where the coefficients satisfy this condition 2cx plus 3cy plus cz equals 0 is a conserved momentum. We are checking option 2, which is given by m times the quantity 2x dot plus y dot plus z dot. Our goal is to express this in terms of the canonical momenta. The definitions for px, pi and pz are provided. Using these definitions, we derive expressions for m times the velocity components in terms of the momenta. As shown, this requires rearranging the definition for bz to solve for my dot. Now, we substitute these expressions for mx dot, my dot and mz dot back into the formula for option 2. After substituting and combining terms, we arrive at the final expression for option 2 in terms of px, pi and pz. Now we compare p2 equals to px minus 2py plus 2pz with our general form for a conserved quantity p equals cx px plus cy py plus cz pz. We can see that for option 2 the coefficients are cx equals 2cy equals minus 2 and cz equals 2. Let's check if these coefficients satisfy the conservation condition we found. 2cx plus 3cy plus cz equals 0. Plugging in the values 2 times 2 plus 3 times minus 2 plus 2. That's 4 minus 6 plus 2. And indeed 4 minus 6 plus 2 equals 0. The condition is satisfied. This confirms that option 2 represents a conserved momentum for this system. So based on our calculations and verification, the conserved momentum is the quantity given by option 2, which is m times the quantity 2x dot plus y dot plus z dot. The final answer is option number 2.